Good evening, guys. Good evening. Very good evening to you. And today we have the 26th August ka problem, and I will discuss the solution. So, if you have not seen the problem, please go to the problem and then see the solution. Okay. So it's a small request so that you can do the problem first yourself and then can see the solution. Okay, perfect. So coming back to the problem, let's discuss the problem. Uh, if you see the problem close, it's related to something called Bayesian. Okay, perfect. It's something called Bayesian statistics, and let's try out this problem. It says that the conditional depends upon it's based on the idea of conditional distribution, and of it's a part after the part of joint distribution that we are doing in the class right now. And what we do is the following, that we um, will actually solve the entire thing thoroughly, and I will help you to understand why this is a really important problem in a statistical sense also. So let me write it down. So I was solving it myself. So it's given that x given theta follows, it's given x given theta follows binomial n comma theta. Okay, and this theta parameter in itself, is a random variable. So we need to find the marginal distribution of x. That means we need to find probability x is equal to x. And you can understand x is a discrete variable. Only the parameters is a continuous one. And if you remember that beta distribution is actually taking value, the support of the beta distribution is between 0 and 1. So that's a perfect um, distribution for probability parameter, okay? So that's why theta follows beta. Theta follows beta p comma q, that's given. So how do you use the marginal? Use the marginal, what we do is that we write down probability x is equal to x given theta is equal to y. Okay, and if we do the conditional part, probability theta is equal to y, that means probability x is equal to x and theta is equal to y in that sense, dy, and we do an integration over the y. That means the theta is varying, okay? The theta is varying and it can take values from 0 to 1. So that's the basic idea. And we put the values over here. So it's into 0 to 1. Probability x is, this is binomial n comma theta. I hope it's n given over here. Yeah, it's n comma theta. So it's n choose x into theta to the power theta is y. So it's y to the power x into 1 minus y whole to the power n minus x. Now this probability theta is it will not be probability, it will be f, the density, since it's a continuous distribution. So it's f theta. So it's again y to the power p minus 1. Theta follows beta p comma q. So it's y to the power this and q to the power this by beta p comma q dy. So we got this, right? So if you look into this very minutely, you will see something really interesting. You will see that it's of the form, integration 0 to 1 n choose x bahar aa gaya, y is x plus x into y to the power p, so it's x plus p minus 1, and 1 minus y is actually n minus x plus p minus q. Minus 1, okay, and by beta p comma q dy. Now understand one thing really carefully, is that this is possible to make it, it's possible to make it into a beta distribution itself. Okay, this one. So what we do is the following, is that we normalize it to make it a beta distribution, and this is done by normalizing what? By normalizing beta x plus p comma n minus x plus p minus q Okay, and that will become a very good beta distribution. So, and we multiply with the same over here, beta x plus p comma n minus x plus p minus q. So we get what? We get this is equal to 1 because it's a beta distribution itself. This will go to 1, and we get beta x plus p into n minus x plus p minus q into n choose x by beta p comma q. The good thing is that you can break it up into gamma and stuff like that. You can break this up into gamma and you will get some distribution. And this is actually in literature, it's called beta binomial distribution. It's a very important distribution. And it revolves around the idea of just conditional distribution. Okay, that's it. Just conditional distribution, and which you will learn very soon. So if you're still live and you're watching the problem, it's a 26th August problem. Don't solve the problem right now. I don't see the solution. You can go pause the video. You can see the problem and do it yourself, and then come back to the solution. So it's an application of conditional distribution. So this part is done. The marginal distribution of x. And let's do the theta given x is equal to x. This is a posterior distribution. That's where Bayes theorem comes in. So it's given that x given theta follows binomial n comma theta, and theta follows beta p comma q. So we have to find out theta given x, and this is where Bayes theorem comes up. So we have to find f of theta is equal to small y given x is equal to x. So you know this is by conditional distribution, you know that this is equal to what? It's f of x is equal to x, like probability of x is equal to x given theta is equal to y into f of theta y, okay, by probability x is equal to x. And understand, we need to find the whole thing in terms of y, okay, not in terms of x. So this is below is a function of x, okay, so we can forget it. I will tell you why we can forget it. Not forget it, but we can make it an easier stuff. I will tell you why. This is a very important idea. The idea is that this is proportional to, so we can ignore this for some time. It's proportional to the initial part, f of x given theta. So probability of x is equal to x given theta. We know that's binomial. So it's n choose x, theta to the power y, and 1 minus theta whole to the power, sorry, n choose x, theta to the power x. Sorry, what I'm doing. N choose x, y to the power x into 1 minus y whole to the power n minus x into f of theta of y. That is the distribution of this. That's exactly the binomial result. This one. Okay. This is the result you will get. And you will get that it's proportional to actually, so f of theta, if you write it down, you will see that you will get it's equal to some function of x over here, some function of x into this part. Why? X into there is a binomial beta part. This beta part comes out, that is y to the power p minus 1 into 1 minus y to the power q minus 1 by some constant of pq. So you get it's proportional, it's equal to some g of x, some function of x into the same thing, x plus p minus 1 into 1 minus p n minus x plus q minus 1. Now understand x is a fixed number over here. So what we get? We get f of theta this is actually proportional to y to the power x plus p minus 1 into 1 minus y whole to the power n minus x plus q minus 1. Beautiful aspect is that there's only one distribution proportional to this, and that is exactly the beta distribution. So you can tell without doing the computation of here, this weird computation and cancelling out each other, you can just tell from here that theta given x is equal to x follows beta distribution x plus v comma n minus x plus q. Just direct. I think there's some mistakes over here. No, I think there is no mistake. I think I did a mistake over here. Did I? N plus, there is no p over here. N plus x minus plus q. Yeah, there is no p over here. So that's the basic idea. So you can directly tell from there that without computation of the x's, that the distribution of theta, the posterior distribution of theta, theta given x is equal to x follows this beta. So this is the idea, this is a normalizing idea, and this is a very important idea when you will learn, when you will do conditionality of conditional stuff, because it's a very, 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 very important idea. Okay, and you will use this over and over again, and this is super useful actually. Okay, so what is the so for what you learned how to do the application of conditional distribution and how we can do the posterior distribution in an easier manner. Okay, so without computing the x stuff, without don't not considering the x stuff, considering x stuff is a constant, you can just see the distribution of y in terms of y, that function in terms of y, and you can tell from there that only one distribution still exists, that is the beta distribution, and therefore theta given x is equal to x follows beta because x is the constant. And this is one of the most important strategy to find out the posterior distribution. Okay, but here there is no posterior or stuff like that. Here you're using just Bayes theorem and basic conditional distribution. So I hope you enjoyed this, guys. I hope you enjoyed this, guys, and let's enjoy the problem solving and do like and subscribe to our channel. Yeah, all the best. And yeah, check out the we are solving a problem every day to make it into a habit. So all the best to you guys, and yeah, see you tomorrow with a new problem. Good night and stay blessed, stay tuned. Bye.